So I can start. So hello everyone, welcome to my talk. I'm happy to share our research on behalf of five, François, Luis, and Stefano. Ke is here. You can also ask her questions. So the research topic is to have a system performance evaluation of RIS-assisted cellular network. There are MIMO-OFDM physical layer technologies I will explain in the system model part. And our technique is based on Matern Cluster Process, which is a two-level Poisson Point Process. And this seminar is going to be divided in 5 parts. I will briefly introduce the RIS in the introduction and give system model performance analysis as our main contribution and give some simulation results and some takeaway. So what is RIS? RIS is in recent years, RIS is a very hot topic in 6G. From a physical layer, it is assumed to be some magic surface that can reflect signal from either base station or from some user to the receiver, to the receiving user of the base station. So we see here it can be deployed as a secondary signal source and connect the base station to the user if they are not well connected. But we look at this technology from system level. From system level, we abstract it to say RIS provide a secondary passes that sends the identical signals the same as the base station to the user. So it's the same signal and by different passes. Specifically, we assume it can be plannable and controllable. This kind of abstraction share some similar ideas like previous generation, like relay, but it have some advantage. It is assumed to be cost efficient because it's cheap and it costs low energy consumption. So here is some background of this technology. So what I mean, some background. I mean, in a system level, RIS is not a brand new idea. It provides a secondary link, but there are many technology provide such type of links. From about 14, 15 years ago, from the release 10, 3GPP release 10, wireless relaying has been standardized, which provides these secondary sources. It is divided into amplifying forward or decoding forward relay. And this technology keep on evolving. So if you look at the left side branch, the amplified and forward relay become smart repeaters and then become network controlled repeaters. It repeats the same signal by same analog signal, and network control repeater can provide some beamforming functionalities. And then the right-hand side, the decoding forward is a real secondary source. We're not going this direction. And then people realize relay or like other type of densification, it costs a huge amount of energy. And energy nowadays is a serious issue. So people propose that why we do amplify? Is there any other way to do amplification? And then people realize we can do some beamforming. This idea can go back to Archimedean times. They have some lenses to do beamforming. Then comes to this idea, RIS system level idea is it can be reflective or transmissive beamforming. It provides a smart radio environment to say if you install a lot of RISes, you can program the reflected beams towards the target direction. And some advantage is sustainability and low expenditure operational capitals. Then with this system level view, we have some open questions on how should we deploy RISes. So since RIS can reflect signal, how can we evaluate these gains provided by large-scale deployment of RISes? Because in this case, there are reflected signal, this composite, many reflect signals, and many system level interferences. So in this work, we provide method and framework to compute coverage probability and ergodic rate under some assumptions that is used in research. And then we further answer the question how to quantify the gain provided by RISes in case some of the links are blocked. And so our system is to provide answer to these questions. And so perhaps I should stay. I should here. So our main tool is stochastic geometry, and one of the major player in the stochastic geometry is Poisson Point Process. I'm not sure everybody knows that, so I have some preliminary give some preliminary here. So Poisson Point Process is random located point set. There are two characteristics. One is in each set, in each like this window, the number of the points follows the Poisson distribution. And then another characterization is in each disjoint set, the number are independent. It's pretty naive, but it provides tractable analysis. The most attractive one is this the short noise field. If every point send some signal, some mark that are drawn from this f function, then you can compute the sum of them in a very convenient way by equation 2. And we will going to use this equation 2 again and again in the following. Okay, we come back to the RIS-assisted cellular network. We have some intuitive background. So why we model the system by Matern Cluster Process is based on this intuitive background. In real world, the placement of base stations and RISes are essentially randomly distributed. They are irregular. We cannot say it's like the hexagon cells. And another constraint is RIS should be deployed in the proximity of the base stations because it has to be controlled. Then the user are also randomly located. Otherwise, it violates the rule of mobile user. And in practice, some links can be blocked by buildings, trees, some blockers. Here we consider a very naive blocking model to say some links are blocked, some are not, with some probability. Okay, put it formally. Here the model is like this. The base station and the user, they're equipped with multiple antennas. Each RIS has many reflective elements. The base station, like this red stars, it's the center of the cells. Around the base station, there are many RISes follow a secondary Poisson Point Process, which is the definition of Matern Cluster Process. They are clustering around the base station. Then the users are randomly located, another Poisson Point Process. So there are 3 Poisson Point Process. Then we assume each user is served by its closest base station. And this allows us to only analyze one user because this user is typical user, and the other user follow the same, perhaps follow the same ergodic characteristics. Then we model the blocking probability for direct link as QD, and for the reflecting QR, we say it's either blocked or not blocked. It's binary cases. Then I will introduce a RIS model. So again, we analyze the system. We analyze the performance in system level. So this is only one-page discussion on the RIS to say the RIS can either reflect or refracting or scattering. There are many physical implementations. So we don't consider that detail. We only assume it isotropic reflection or refraction. It either reflect or refract. It doesn't matter. You can refine this model to say it's only reflect by by changing the density, by subsampling the density of the isotropic RISes. Then the equation 3 is like a it's like an antenna array to define how to do the beamforming. But we won't go to that detail. So the takeaway of this page is we assume a very simplified beamforming model to say each RIS in each cluster, they are separated into small batches, and each batch to form a small beam towards a typical user. So the takeaway is this small beam. Then the base station sending signals. The RISes reflect signals. So we have this equation 4 as the channel model. Here, we assume each link is represented by one tap. One tap means if you send a very narrow impulse by the base station, there are some impulse response, and in traditional signal processing, this is called taps. And there are two types of taps. One is direct signal and one is reflective signal. Reflective signal is made by first the base station to the RIS, and from the RIS to the user. And each tap has a time delay because of the radio propagation. So this time dispersive channel, this time dispersive channel requires some modulation technology, and we assumed OFDM. So OFDM is very okay. So the OFDM is widely used in either 3GPP or Wi-Fi. It's a convolution of the signaling train and the channel taps. Then in the lowest level, we have to go to the specific definition of channels. We assume for each leg, for each link, there is two factors to determine the channel. One is the signal power attenuation by the distance dependent model with path loss. Then there are fadings. We define for each leg there is independent fadings. They are denoted by rho. And then there are cases to describe the blocking probability, to say the direct link can be blocked with probability QD, and they will receive some penalty. For the reflected link, we say the RIS form a very narrow beam towards the user. We'll assume if it is blocked, then this beam is canceled. Then I will provide the main steps to analyze this system. There are two parts. The first part is to analyze each link. Then the second part is to combine all the links together to the whole system. So this is the first part, is how the receiver antenna is going to process this multipath links. We see here, this row denotes fading for individual links. So for when one path is reflected by one RIS element, they compose a composite fading, we denote it as zeta. We can characterize the distribution of zeta by the product, by the multiplication of random variables. But then we see each RIS have many small elements to form a beam towards the user. Then the fading for this beam is going to be the sum of many zeta. Then thanks to the central limit theorem, we can characterize this fading chi by non-central Gaussian random variable. So there are not only one RIS reflected signal, there are many. So how to merge them together, we considered OFDM. And the OFDM would have some demodulated channel gain and send it to the user. The user would combine the demodulated gain from different antennas together using the MRC. So the first step is OFDM signal processing. OFDM is also a very old technology from maybe 50 years ago. It basically says you map the convolution of channel signals into the frequency domain, so they can be treated as parallel subcarriers. We won't go very deep. If you are interested, we can go some standard textbook. But the result says, because of the Password theorem, the power of the effective channel gain for each antenna by demodulating the OFDM symbols will be the sum of individual channel taps. We see here, this HD is the direct channel taps. This is the channel taps from all the reflecting, from all the RISs. Then the next step is, so there are multiple antenna, and the output of the antenna is sent to the central processing unit, which can perform the maximal ratio combining. The maximal ratio combining requires some knowledge to perform the signals. Then usually we could ask the base station send some pilot symbols, so the user can estimate the specific link for the associated base station. So in our case, we assume this the combining policies, this weighting matrix is linear to the HS, the channel associated with the signal, and they are agnostic to the channel of the interference. And this allows, the result of this is the output of this MRC is the squared norm, the squared second norm of the signal, but some post-processed signal of the channel of the interference. Then we can begin to analyze the distribution of individual links. Here, by equation 18, we normalize the channel by its path loss. So each channel is each link can be characterized by independent and identical and independent distributed random variables. For direct signal, we denote it gamma SD, and for reflex signal, it's SR. For the direct link, it is very straightforward, because once we assume each antenna receive relay distribution, the sum of the power will be the gamma distribution. This is a very how to say this? It can be assumed as background knowledge, but for the reflected beams, it would be something we need some careful attention. There is very few established results. What we did in our research is we say the composite fading is the sum of many small-scaled product fading. Then, because this beam is formed by many small antennas, you can use the central limit theorem to approximate this chi for this one antenna. But for the other antenna of this receiving devices, they are also in the same beams, but it's very hard to say they also have the very same gain. So we assume the other antenna receive discounted gain, and the result is the power of the reflecting fading random variable would be a chi-square distribution. Well, what is favorable here is we have this distribution can be easily characterized by its Laplace transform, and we will see why this is very favorable. Then is the maximal ratio combining for the fading of the interference. For the fading of the interference, since the RISs in the other cell would not do beamforming towards the typical user, and the scattering effect from the other cells would be trivial. So we neglect this part and only consider the main tap from the other base station. Then this is a result from the OFDM demodulation. And one result which is pretty important in the paper that's going to be neglected here is this MRC signal processing. This is the inference channel, and this is the weight, and these two are agnostic to each other. So with so this is actually a splitting, can play a splitting effect, and the result is pretty amazing, because if you remember for the signals, the post-processed signal follows the gamma distribution, and the scale is depends on the number of receiving antennas. But here for the inference, the power will be invariant, follow the invariant exponential distribution, because no matter how much antenna you have by the HI perceiving the inference signal, they are going to be split by the post-processing weighting vectors. If you are interested in this is very interesting, but it can go to a side talk. Then we have that many random variables. We would have this analytical result. Don't be panicked, because we're not going to remember these formulas. This is a final result, but it's going to be derived by 3 steps. Of course, there are start and end in function definition, but you will see there are only 3 main steps you can derive that complex formula. The main step here is we are going to define what is coverage probability, and then we will do some very basic algebra manipulation, and you will see the coverage probability can be expressed by the modified function, and it can be directly evaluated by the Laplace transform. And these components in that formula can be expressed in Laplace transform in the preliminary slide. And the main contribution will be the 4th step is we show how the modification can be done analytically. Then you will come back to the first analytical result. So for the typical user, the coverage probability is defined by, say, the SIR. We neglect noise here. The SIR exceeds a target threshold T, which is going to be the equation 27. Once we condition on the distance of associated base station as the user to be R, we could have this expression, the expression over this R. But to say the sum of the direct signal, sum of reflected signal, that divided by all the inference is larger than this threshold. Recall that we also assume the blocking, the complementary blocking event. It either blocked, non-blocked, and blocked. This is a constant, so we can only analyze the formal part. So this is the equation 29 is going to be the very important manipulation. Is we first move the denominator to the right-hand side here, and then the QSR to the right-hand side here. To see here is a minus. This is going to be the main challenge. Then what we do is we can evaluate this probability by analyzing the characteristic of left-hand side and the right-hand side. What we are going to be interesting is if we take this right-hand side by one random variable, it is going to be very favorable to analyze it. So we see why. Why is so? Perhaps for people who are familiar with stochastic geometry, you must have seen it many times. I just give a very quick overview. Is for the direct link, this is a single link. This is the fading, power, and path loss larger than one component. If you move this constant to the right-hand side, it's going to be the one random variable larger than this. And this is going to be the CCDF, the complementary CDF. In our case, this gamma SD is gamma distribution. Then this gamma distribution can be written into some manipulated term of the exponential and functionals. Then here is the magic is by the definition of Laplace transform, unilateral Laplace transform, this part can be written into this part. This is Laplace transform notation. But one challenge arose here is we only need its positive part, but record the minus here. This gamma is defined on the whole real axis. It's not only positive. So this is the new challenge brought in our research, which never occurred in previous stochastic geometry before. So what is the expression of this epsilon? We see it's a minus of the composite inference minus the composite signal. And perhaps it's the sum or subtraction of random variable is a convolution of the density function. And the convolution in the Laplace domain, or more specifically in the frequency domain, is going to be the product of the two. So we could write the bilateral Laplace transform of this epsilon is a bilateral Laplace transform of the product of the two. For each one, recall that we say the Poisson Point Process can be written into these functionals. For each one, it's going to be derived by these 3 or 4 equations. This QIR, the interference field, or the QSR, the reflected beam field, following the same way. And the result is we have an analytical expression for this epsilon, which is defined on the real axis. But we only want its positive part. And here the main contribution in our work is we provide an analytical function. This is a singular type integral from the minus infinity to very small zero, this epsilon, and from epsilon to positive infinity. This is in the sense of Cauchy principle integral. So with this formula, we can directly separate the Laplace transform functionals. And even for higher order derivatives, you can directly apply Leibniz rules. So far, so good. Okay, so if you merge these 3 steps together, you will have the analytical result of coverage probability and ergodic rate. So here is some simulation analytical result and simulation result. So here is the configuration of the simulation. The density is set as there are 10 base stations per kilometer square. And the cluster around the base station is set as a ring, which is the inner radius is 10 meters and the outer is 25. Then in each cluster there are in average 5 RISs and 5 users. Then you share the resources, and we consider there are 1 or 2 receiver antennas. Then one point to specify that the analytical method is done by evaluating the analytical expression by numerical integration. So the benefit of the analytical research method is to do this Monte Carlo method. For example, here we perform 1 billion times to generate the points and compute the SIR and then derive the coverage or ergodic rate. It takes perhaps hours. Then for the analytical result, it only takes about 1 minute. So here is some results to talk about the performance. So here is for the coverage probability at a cell edge user, to say the user is located at a distance of 200 meters, and the coverage threshold is set as 1. Then we vary the number of RIS elements. So here, when when the number of RIS elements is 0, we say there is no RIS. And with the increase of the size of RIS, we see the coverage probability increase. Then we also see sometimes we specify 2 cases. The QR as 0 means there's no blockage for the reflect beams. It's always superior than the case where the QR is 0.4, implying that more RIS is always more beneficial. Then this is the same result for this is an ergodic rate for the same setup for the coverage probability in previous slides. However, here we have to say the analytical result is done with some limits. It's not infinite because it's still a numerical result. And we say the risk can bring some benefits in the scale of some 10%, not some fold. So for example, here you see when each RIS have 400 elements to do beamforming to the user, the gain can go up to 45%. So it's already a huge RIS, but very few. The gain is pretty moderate. And then there are some missing parts. Is because if you want to do the analysis analytically, you have to ensure the Laplace transform converge. But sometimes it doesn't converge because it's mathematical characteristics. Then
you say that it doesn't convert. Is it numerically?
No, it's analytically. Yeah. So if you remember the definition of Laplace transform, it's going to be the integral from -infinity to positive infinity. Then if the density function itself doesn't converge, then it doesn't converge. It's some constraint from the math part rather than implementation part. So okay. So so we say the relative gain provided by RISes is not very significant for homogeneous cases. Then we investigate the case that the direct link is severely blocked by introducing penalty. Then we see the relative gain keep on increases with the blocking penalty. The takeaway from this slide is to say, if you want to implement RIS and you expect benefit, huge benefit, you better to exploit it, to deploy it to help the user that are at some dead zones, at some zones that the direct link is so bad. Then we also do some investigation to understand the influence of the geometry of the RIS cluster. Recall we say the RIS is randomly distributed around the base station. But we finally find out that the RIS should be deployed as close as the base station because the reflected path is made of 2 legs. Each leg have severe path loss. So here we have some comparison to say the outer radius, if it is larger, then the performance become worse, or the inner radius is larger, then the performance is worse. So the takeaway is the RIS should be deployed as close as possible to the base station. Perhaps the final result would be the massive MIMO. Some of the antenna perform beamforming some actively sending signals. Okay, and then we explore some way to allocate the RIS resources. One thing to specify, this is one disadvantage of RIS is you cannot reuse the RIS resources, because if you do analog beamforming, the phase shift of this elements are once it configured, it cannot be shared to others, like the modulation technology. So perhaps the takeaway here is we should use many. We should use the one huge RIS and then serve few users. So here is some conclusions. The conclusion is divided in two parts. One is for the RIS. So RIS can be effective in specific case, then the direct link is blocked or the RIS is huge. Then RIS should be deployed very, very close to the base stations. Otherwise, the path loss would be very severe. And then if you have the same amount of RISes, it's better to have one big RIS to do very strong beamforming rather than allocate it into smaller RISes, but to do many small beams. Then in terms of the stochastic geometry, we introduced this called secondary sources that transmit identical signal beside the primary source. Then in our work, the highlight is to model the reflect signals as a short noise field, in addition to the conventional case that only the inference is considered as a short noise field. Then when the signal and inference compete with each other, it is modeled by difference of two non-negative random variable. Then the challenge arises, say the resulting random variable is defined on the whole real line. Then coming back to the coverage probability, you will have to separate this random variable in the middle. You only keep one part and not the other part as 0. For this purpose, the equation we provided can be understood as a multiplier operator in the operator theory. And the remaining analysis is pretty standard. And a very high-level takeaway is previously we considered point-to-point communication, that you specify one transmitter, one receiver, and you analyze the characteristic of this link. With this modeling, you can analyze the field-to-point communication. It is to say the signal sources is distributed rather than centralized. So of course, you will require some signal processing technique to combine these spatial diversities. And then the remaining procedure is the same as the previous method. So that's all of my talk.
Thank you. Any question in the room?